starting over again. Let's review some facts about exponents. And let's say that I have a squared and I raise it to the third power. Are you taking notes? I would like it if you wrote all this, but I'm about to write down.
I want to write it down after you finish because I can't keep up.
Okay, so this right here is a squared is a times a, right? To the third power.
Yeah.
And that right there, right, raising something to the third power means we take whatever it is and multiply it by itself 3 times, right? And so then we have a times a times a times a, right? But we could regroup this if we were so inclined. We could say, well, you have a total of, well, how many a's do I have there?
6.
Right. And so I could regroup it into groups of 3 like this and say, well, wait a second, that's the same thing as just a cubed times a cubed, which is just a cubed times itself, which is just a cubed squared, right? Now, another thing one thing to notice here in the middle is that this is the same thing as a to the 6th, right? You just have a total of 6 a's, which is the same thing. And this is where it all came from, right? 2 times 3 is 6. This is the same thing as a to the 2 times 3 right there. Now, right, this is just review. Then this is, of course, you know this stuff, but we're going to put this into play. We're going to put this into action today to get us something that we want, right? So kind of summing up what I just said here is that if you have a raised, in this case, to the 2, and then you take whatever that is and raise that number to the 3, it's the same thing as just saying, well, it's a, right? How many a's would you have? Well, I have 2 a's, and I'm going to do that 3 times. That's just 2 times 3, or 6. So in other words, a to the 2 times 3, which we could even rearrange if we wanted to, if it's for whatever reason beneficial to us, to rearrange that and say, well, instead of grouping that in 3 groups of 2, I could group it into 2 groups of 3. And so this really the same thing as a to the 3rd, but then raised to the 2nd power. Real trivial stuff when you're talking about whole numbers here. In fact, like I could just draw it up on the board and it makes a lot of sense. Like I could see why that has to be the case. And I much prefer thinking about it like this, as opposed to simply memorizing some rule on what to do with exponents. Like, when do I add exponents? When do I multiply exponents? Well, I like to just think about it like this to justify that, yeah, if you have an exponent raised to an exponent, then you multiply them, which we can see that's why you have to do that. And in general, now this is the thing, it doesn't matter if I did 2 and 3, right? Like if I had a raised to the nth power, and I wanted to take whatever number that is and raised it to the mth power, then this would be the same thing as taking a times a times a times itself a total of n times, and then raising that to the mth power. And so then we'd have m groups of n a's, right? You have n number of a's here, n number of a's here, and we can do the same thing and rearrange them. But the rule stays the same, right? If I have n a's and I repeat that a total of m times, you're going to have the total number of a's that you end up with are going to be n times m a's, which you could then regroup, right, into a to the m, and you have a total of n of them. Are you following?
Yeah.
Yeah. I'm taking a look. Oh, yeah, that's right. That's Kayla. I'm sorry, buddy. We got to teach right now. I'm sorry.
Light.
How about a quick hug? Quick hug. Love you. Yeah, love you. Okay. So ultimately, the important thing here is the formula that we are going to be using. And I went through all this and ate up a good 5 to 10 minutes of talking because it's real important to not think about this stuff as a formula, but I like to think about it visually like what we just did. So if I have a to the n, I have n a's, and then I take that and repeat that m times, then the total number of a's that I have that I'm multiplying by each other is just whatever n times m is. Since that's the case, I can regroup that into groups of m, and I will have a total of n groups of m. And this is going to be really useful for us for today, for our conversation. And for the rest of your life, because math is so important. You need to know this stuff for the rest of your life. Okay, now we're going to use this in a minute. But right now, let's just take a little side trip and say, let's say I have the square root of a. Take the square root of a. And then I take it and square it. What does that equal to?
Isn't it just equal to a?
Exactly, it's just a, right? And let's just really drive this point home. If I took the square root of 9 and then I squared it, well, let's just see what would happen. You'd say, okay, the square root of 9 comes back to 3. And so you'd say 3. Yep. Then you'd square that and you go, yeah, oh yeah, you ended up right where you started, right? These are inverse operations. It's like saying, take a number, add 2, and then subtract 2. That's what we're doing right here, right? This will always bring you back to here. By definition, that's what it does. Now, our goal today is going to be to rewrite something, a root of something, right? So some number, the square or whatever root of it, we want to write it as that number to some power. Right now, we don't know what power that is going to be. But what I'm going to do is say, okay, well, if we could do this, if we could justify this kind of thing, then the rules of exponents are going to have to be the same as these exponents right here. So what I'm going to do is say, all right, you know what? Instead of writing the square root of a in this equation, which we know has to be true, I'm going to replace this with a to this unknown power. I don't know what power that has to be, but that's what we're going to do. So basically, our game now is going to be to find whatever p is. We want to know, what is this p? So let's use this nifty little fact that has to be true, right? This has to be true when we have whole numbers, right? That if you take a to the n and raise it to the m, the total number of a's that you have has to be n times m. So let's use that fact right here. And we're going to say, okay, then a to the p raised to the 2. So in other words, a to the p times a to the p is just a to whatever p plus p is, or in other words, 2p. You have that many a's. 2p equals a. Now here's the trick. We could say, well, wait a second. What's a just by itself? A is itself to what power? Kind of tricky.
0.
0. Anything raised to the 0 is just 1. So like 2 to the 0 is 1. 3 to the 0 is 1. But 2 to the what power equals 2? Say what?
Wait, what?
2 to the what power equals 2?
Is it just 1?
It's just one, right? This is what I mean. It's tricky. The way I was asking that was tricky. But yeah, the only way to get a out of a to some power is to raise it to the first power. You're like, shut up, Justin. Of course that's true. Well, yeah, but this is what's going to help us out. Is we could say, well, wait a second. Then these things have to be equal. If these powers, I mean, if a raised to some power is equal to a to the 1, then it must be the case that whatever this is has to equal 1 right there. And so it must be the case that 2p is equal to 1, and therefore p is equal to what number?
Hold on a second.
Okay.
Mm, 0.5, or I guess 1/2.
Half. We could write it as 0.5. I'd much rather use fractions in this case.
Mm-hmm.
And so that is what we were after. We're trying to justify rewriting this thing as a power. And what we have found is if we can even do that, which we can, then the power it has to be is 1/2. Now let's just see if this makes sense. Let's just rewrite this and use some rules and see if this is at all consistent. What we just said was that, well, we know that this is true, so let's verify. If I have the square root of a squared, I'm saying that we can rewrite a square root as that number to the 1/2 power. So I have a to the 1/2 twice. In other words, that whatever that is squared. But our rules, excuse me, says that if you have a number raised to a power and you take that and raise it to a power, it's the same thing as taking whatever that first power is times that second power. What is 1/2 times 2?
1.
Hey, look at that. It's consistent. That's what we should have had. And we can see that this is going to work for any root that we have, as a matter of fact. So just to drive this point home, let's do it one more time with a cube root and see what we end up with. Well, I didn't bother to ask if you were done copying this up, but we're just going to go ahead. Okay. So let's do the same thing with the cube root. I take the cube root of a and then cube it, and I get a, right?
Yeah.
Yeah, so let's do the same kind of thing. Let's say, okay, what we want then is to rewrite the cube root of a as a to some power. Let's, instead of calling it p, let's call it q, so we're not messing things up here. So a to the q, then, just going to rewrite that as a to the q raised to the third is equal to a by our fact that we have up here. This formula says, well, then this has to be a 3 times q, right? Multiply those guys together. So we have 3q equals a to the first power. That implies that 3 times q has to equal 1. How do we solve for q? What does q have to equal?
1/3.
1/3. And indeed, this is going to work for any power of, or any root, right? Because if you take the, let's just say the kth root of a number and raise it to the kth power, and you want to know, well, how could I rewrite this thing as a to some power, let's call it r, what would we do? Well, it's the same kind of thing. We would just say, well, instead of writing this, we would write it as r. Then this comes out to, oh boy, k times r, which is just
Whoa.
Do you want me to shut up?
No, I'm good. We're good.
Okay, cool. So this is and this is we're aiming at something general here. We're saying we want to rewrite a root as something to a power. Okay, so I'm just blindly going to replace the symbol right here and see what happens. By this, we have to have it so that that equals that. So we just multiply them together. Well, then KR has to equal to 1. And it's R that we're looking for. We're trying to solve for R. And so we get R equals 1 over K. And so we get A to the 1 over K. So that is what we're after right there. It's that the root of any number is equal to that number 1 over whatever the root is. And so this is the same as A to the 1/3. The square root is the same as A to the 1/2, and so on and so on. And it's really the only way to make all of this stuff consistent, right? Because what we've now done is we've introduced rational exponents. Exponents up until this point have always been whole numbers. And it's really nice to work with, because if you say even something crazy like, I don't know, 3/5, when you square it, you have a good idea of what that means. If I take 3/5 and square it, that means just take whatever 3/5 is, multiply by 3/5. Okay, that's nice, right? And you could do that. That would be 9/25 and so on and so forth. But now, when you say raise something to a fractional power, it's like, what could that mean? Well, we want all of this to be consistent. We want these rules to still work, right? And so that's what we've kind of demanded. But we found that this is what it means to have a fractional exponent right here. Is that if everything's consistent and all these rules still apply for fractions or for whole numbers, then it has to be the case that 1 over some number is actually the root of that thing right there. And I can tell you, it is sometimes very convenient to be able to take something that's written like this, right? Like the kth root of something, and rewrite it as something to a power right here. And that's what this is all about. So now that this was all really to get this. Your book just says this equals this. And okay, like you could just take that on faith, but this is why it has to be that way, right? And that's, yeah. So does that make sense what we've talked about so far?
Mm-hmm.
You see why it has to be the case. Make everything consistent. Okay, so moving on. Since that's true, okay, then we could play some game. And I'm going to leave this up here because this is going to come up a bunch of times. And just because now we're talking about rational numbers, right? We can't have different rules for exponents just because now we're using rational numbers instead of just whole numbers. And so this is going to have to be this fact right here is going to have to be true, even if you have, say, a to the 1/2 raised to the 3/7. It has to be the case for mathematics to remain consistent that this is the same thing as a to the 1/2 times 3/7, like that. And then there's a bunch of different ways we could go from there. In particular, let's just look at this. Well, then that also has to mean that that's a to the 3/7 raised to the 1/2, like that. Really, all I've done is I've just replaced n with 1/2. And everywhere I saw an n, I put in a 1/2. And everywhere I saw an m, I put in a 3/7. And that's how all this kind of pieces together. And this is what we're going to be playing with today. So your book gives you, it's called Theorem 7.6. And that is basically what it says. It says theorem 7.6. This is equal to, is that what it does? It is what it does, yeah. It says this right here. And putting it in this language here, with thinking about this as a fractional exponent, well, this is what this means. We're just saying, okay, you're taking a to the m, and instead of now having a root right here, we're going to rewrite that root as 1 over k, like that. But that's the same thing as a to the m times 1 over k, which we could do in the reverse order, right? Because it's exponents have to play this game. They have to be consistent here. So in other words, we could flip the order of this thing and go 1 over k raised to the mth power, which is, oh, hey, what do you know? Exactly what that says right there. That says a to the 1 over k means the kth root of a, right there. And then we're raising it to the nth power. And going all the way back, right, you see I just started with that right there. That's just a to the m. And the k to the 1 over k means take the k root, the kth root of it. So this is the reasoning behind that theorem that's just stated like this. This is why it has to be the case, because if it works for integers and we're going to extend our definition to include rational numbers, well, it had better follow the same rules. Otherwise, all of math is going to come toppling down around us, and then bridges are going to fall down and we'll sink into a black hole and all kinds of bad stuff, right? We have to have all this stuff be consistent. And so, you following so far?
Yeah.
This has been abstract land, right? Like we're giving you very general definitions of stuff, and it's like, why would I care how we write it? Well, this is why. Let's do some examples. So first off, first part of the very first part of the assignment, parts 1 through 8, or numbers 1 through 8, it says to use this theorem right here to simplify, or rather, it says simplify these things as shown, then use this to simplify in another way. Just on your homework, do it however you want. You do whatever you want with this. I would like to see you change them into fractional exponents, because that's kind of the name of this game. But here's the idea. So here's one of them, number 2. It says square root. Where was it? Square? Yep, square root of 7y raised to the 3rd power. And what your book is, or what this question's getting at, it says to simplify. Hey, buddy. Now, if we hadn't thought about anything we'd learned today, we could do this the way that we've been doing it. You say, well, if you have 3 of something and it's in a square root, then that means I get to take 2 of, for every 2 of them that I see, I get to pull 1 of them out. And I would have a 7y up front. And I would be left with 7y left inside. So that's how we've been doing things up until now, right? But another way we could do this is to say, well, this is the same thing as, instead of writing that as a root, we can write that as a fractional exponent. And so we could take this guy right here and say, oh, that's the same thing as 7y raised to the 3/2, right? I just multiplied those 2 numbers together. I just used this fact right here. And from now on, for the rest of your life, whenever you see something like this, you could just immediately think, oh yeah, whatever the number is in here, And whatever root this is, and this was, the theorem that we just had, a to the m k is the same thing as the intermediate step is that's a to the m over k. And so raised to the third power, the square root is the same thing as 3 over 2. Now from there, a few different ways we could go. And let's think about this, because we've done this a bunch of times. Like if we have x cubed and we're trying to take the square root, we've been breaking it down as x squared times x, right? Which we know we could do because, well, it's a total of 3 x's, and I've just regrouped them. And so what I'm getting at is if you have x to the n times x to the m, it's the same thing as x to the n plus m. And this is where that weird stuff with, wait, is it multiply by or is it add? When do you multiply and when do you add? If you think about what these things mean, right? 2 x's and 1 x, and you multiply them together, you have a total of 3 x's. That's what that is. That's why it's plus. We could use that same fact right here and say, well, how many whole numbers can I get out of that? And well, 3 halves. Well, that's 1 1/2, right? Or 1 plus a half. Or I mean, we could, if we wanted to, write it as 2 halves plus 1/2. And that's kind of what we're doing here. We're saying, well, that's 2 halves, 7y to the 1/2, like that. This is what your book is getting at for how to do this part. Doesn't really give you any, doesn't tell you exactly what to, although there are examples in there. So anyway, then we just say, well, wait a minute. 7y to the 2 halves is the same thing as 7y to the 1. So that's just 7y. 7y to the 1/2 is the same thing as the square root of 7y. And that's the answer your book's looking for. This is how we've been doing it. This seems like a harder way of doing it to me. I don't know about you, but it's like this took really 1 step. This takes, well, first you have to translate it. So that's 1, 2, basically 3 or 4 steps. And it's like, it seems harder, but I could tell you being able to do it in both ways will make your life much, much easier. There are plenty of times in your life where you will want to think about it this way instead of like that. And so that's kind of part of what we're doing in this section, is being able to do both, being able to translate between both ways of looking at it. Any questions yet?
No.
Following everything so far? All right, well, let's do this. Oh, here's another. Yeah, I did want to go over this one because so it seems nice and simple now until you get something like this. Here's problem 8 from the same section. And it is the cube root of 9, I believe it's x squared y, all raised to the 2nd power. And so what this is getting at is saying, well, we could do this in 2 different ways, right? We could think about this as the kth root of a raised to the nth power. And if we like, we could go ahead and translate it. But to kind of get to the point here is we could flip this guy around basically and say, this is the cube root of this stuff squared. I just didn't go through that intermediate step where I had like 1/3 and then 2, and then we have 2/3 and then split it so that the third goes on the outside and all that crap. I just kind of went right for it and said, well, we just flip it, flip the order, and it means the same thing, right? And so, okay. I'm sorry. I do want to be explicit about that. Is that this means in here, 9x squared y, the third root of it means you're raising that to the 3rd power, and then you're squaring it, which means the same thing as 9x squared y where you just multiply those guys together. So that's just to the 2/3. As a matter of fact, whenever you see something like this, I know that that's the same thing as whatever's on the inside raised to the 2/3. That's how I see that in my head. Because I know that the root is the denominator, basically. Then from there, we're just saying, yeah, okay, well, since you could do that in either order, that's kind of like saying you do the 9x squared y and then square it, and then you take a cube root. We just flip the order, which finally is just then the cube root of 9x squared y all squared, which is what we have right there. Now for this one though, and so we're trying to, and ultimately we're trying to simplify, right? Looking at it like this does not help me simplify anything, but looking at it like this does help. And so am I good to erase this stuff down here?
Yeah.
All right. Okay. So first off, 9 is what? How can we simplify 9 just by itself? Completely out of context here.
3 squared.
3 squared. There we go. That's usually going to help you. Whenever you're doing problems like this, if you could break something down into its prime factors, it will usually help you. When I did this one earlier, I didn't do that. And I was like, how am I supposed to simplify this one? Break it down into its prime factors. Okay, so now let's just look at the inside stuff here. Let's go ahead and square that out. 3 squared squared is what in terms of prime factors? How many 3s do I have when I square?
2.
3 squared.
Oh,
So
3 squared squared 4.
Total of 4. There we go. So 3 to the 4th. Well, it's kind of the same thing with x squared, right? X squared squared is how many x's?
4.
4. And y squared is how many y's?
2.
2. There we go. Notice what I just did. I just used this, right? I didn't talk about it this way. I didn't say plug this into here, right? But that is what we did. We said there's 2 3s there, and then you have 2 of them. Oh, 2 and 2 make 4, right? And ditto with the other stuff. We've been using this the whole time. We're going to be using it for the rest of our life. Okay. So you reduce this. What goes on the outside and what's left over on the inside? What can I pull out?
You can pull out a 3.
I could pull out 1 3.
one X.
Leaving me how many 3s inside?
1.
1. Okay. What about x's?
You can pull out an X.
1x. Leaving me how many x's on the inside?
X.
And then what about that y squared?
You just keep it.
Got to keep it. We don't have enough to pull any out, and so it stays there. And that's what your book's looking for right there. It's really confusing to me when it says do this 2 different ways. I can't think of another way to do this. Like this is, I don't know. Maybe I'm just slow. Maybe, oh, you know what it probably wanted you to do is take this and square it. And so you have this, and then you square it the way that we have been doing it, like this, to give you, using that nice one that we've been using where the multiply 2 roots together is the same thing as just multiplying what's in there all together to give you this right here. That's probably what it was getting at. And so that would be 9 squared x to the 4th y squared, and so on and so forth, and you'd end up at the same thing here. But yeah, so you're gonna have something like that. I'll just say for these, you don't have to do it 2 ways. Just do it any way you want. Frankly, I would like to see some fractional exponents, but you'll have plenty of work with that. So, okay, am I good to erase?
Mm-hmm.
Okay, all right. Okay, another thing. Now, going in the opposite direction, how do we write something without rational exponents. And let's do this. If I have this right here, what does that equal to? It should be the something root of something, And that's a 5, by the way. That's 1/5.
Okay. That'd be y to the, well, the fifth root.
The 5th root. That's what it means. That's by definition, that's what it is. Because we know a to the kth root of a is the same thing as a to the 1/k. So whenever you just have a 1 over some number, that's exactly what it means. And so 1/5 in your exponent, it means take the 5th root of that thing. So let's make it a little bit more difficult. Let's make that 3/5. Let's start with the root. Let's do the root on the outside.
5.
And it's the 5th root, and then what goes inside?
Three.
Did you mean y
Oh.
to the 3?
Yeah.
Yeah. Y to the 3rd. That's what it means. That's all there is to it. If you're so inclined, you could swap the order of that and do that type of thing right there. That's also true. And maybe sometimes that'll be nice for you. Like if, for instance, y happens to be 32, right? Because I know that the 5th root of 32 is 2, then that might make your life a little bit easier. So for instance, if it were 32 raised to the 3/5, I could look at this 2 different ways. I could say, well, either we could go 32 cubed and then take a 5th root. Yikes, that looks terrible. Or I could say, well, or flip the order. We could say that's the same thing as the 5th root of 32, then raised to the 3rd. In which case I could say, oh yeah, the 5th root of 32 is 2, I think, right? Did I get that right? Because 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2. So we have a total of 5 of them, right? And so then in that case, I could say, the 5th root of 32 is 2. Raise that to the 3rd. That's 8. And so it's kind of nice. Like you'll run into stuff like this. And then now after doing this homework, you're going to be doing this back and forth thing a lot. And then you'll get into the habit of being able to say, well, wait a minute, which one of these is easy? I could either take this and write it like this, or I could write it like this. This way, in this case, turned out to be easy. And so I'm going to go ahead and reduce it that way. Maybe we want it in this way for something else, who knows? But that's the idea. Okay, so moving on. You'll have those guys. Let's see. Hey, that's one. Oh, it's not one of your homework ones. That was actually 32 to the 3/5 was actually in here. So let's do this. I didn't give you that one. So no, I did give you that one. So let's do, I gave you that one too. Let's do this one. Okay. So we want to now go in the opposite direction and we want to write things with rational exponents. So how do I write this as a rational exponent?
17 to 1/2 power or whatever thing.
Go. That's all it is, going back and forth that way. Now, this is where it gets a little ugly. But let's do this. We want to do the fifth root. Okay. Okay. What about this guy? So forget for a second that this is three different things. Let's just consider this all as one thing. And we know that you take a root of something, it's the same thing as that thing raised to a power. What power would this be raised to?
1/5.
1/5. Okay, so we have part of it down. And now let's pretend for a second, because like when I see this now, I think, wait, what are my rules here? Am I adding? Am I multiplying? Does this go into each one of these? I'm not too sure. So let's just use a simpler example first. And let's suppose that we had AB squared and we are going to cube that. I would imagine, okay, that means the same thing as doing each one of these things 3 times, or multiplying this by itself 3 times. Rearranging gives me a total of 1, 2, 3 A's. So I have A to the third. How many B's would I have total?
6.
The sixth. So what we've just done here is we take the first thing, raise it to that power, or in other words, 1 times 3. The second thing, we took the power and multiplied it by that thing, right? And so we're going to have to do the same thing here. Since x is just by itself, it just picks up that power and we just get x to the 1/5. This thing then becomes what? Y to what power?
2/5.
2/5, right? We're just reasoning by analogy. It's like, well, squared, you would just multiply those two. So I'll just multiply those two. That's 2/5. Cool. And then z would be raised to what power?
1/5.
1/5. There you go. And I think in your book, what it's looking for is this right here. Okay, but it is true that this is the case. And I could tell you that when we do logarithms, this will be much better to think about. Like we want to be able to translate between this and this. Your homework's not going to demand that you go this far, but just so you know, like the rules, the same rules apply. That if you take AB squared, raise that to the third power, it's the same thing as taking A to the third and then B squared. So you multiply those guys together. The same reasoning applies here. It has to, otherwise we've just changed the rules for math. We want everything to be consistent, whether the things that we're raising it to is a fraction or we're taking a number and raising it to a whole number. We want everything to jive, and so it has to jive that way. Okay, there's that. Now, okay, so on a slightly, I'm erasing this. Am I good to erase this?
Yeah.
Okay. Now, on a slightly different note, not really that different, but a to the negative n equals what? What does negative exponent mean?
1/8 to the n.
There you go. There you go. Exactly. Right. 1/8 to the n. Now, what about, let's do 1/b to the negative m. What does that mean?
Would that be 1/1/b to the m?
Yeah, we can think about it that way. 1/1/b to the m. But dividing by a fraction means multiply by the reciprocal, right? And so b to the m over 1 And so to simplify everything, we just end up with b to the n. So you're absolutely right. You are absolutely right that it's 1 over that. But we could, but what we're getting out of this, rewriting it by taking that step and then finalizing it this way, I think about this kind of as a rule, which is that a negative exponent simply means, like I think about it as, this means take me to the opposite side of a divide sign and then make me positive. That's all it means. That is the only thing that means. Negative exponent means take me to the opposite side of a divide sign and then make me positive. That's how I think about it. So then one final thing. So this is, if you have a negative exponent in a numerator, you just take it into the denominator. If you have a negative exponent in a denominator, you just take it up to the numerator, right? If you're upstairs, you go downstairs. If you're downstairs, you come upstairs. Finally, let's look at this. What if you have A over B raised to some negative number? Let's call it negative NM. How about LJ? How about P? Negative P. Uh-oh. Well, this means, let's just think about it, right? Some number raised to a negative power means take me to the opposite side of a divide sign and make me positive. So I'm not using my brain here, right? I just said, well, this symbol comes down here and then we change the negative to a positive. Okay, so that's all I did right here. Boom. But this is the same thing as 1 over, how about A to the P over B to the P? And dividing by a fraction is the same as what?
Multiplying by a reciprocal.
And so what do we end up with here?
B to the P over A to the P.
Which we can rewrite like this. B over A all raised to the P. Sometimes it'll be nice to think about it like this. Sometimes it'll be nice to think about it like this. But the rule here, so have something in the numerator, raised to the negative power means take me downstairs. Have something in the denominator, raised to a negative power means take me upstairs. Having both upstairs and downstairs raised to a negative power simply means flip it. So A to the B to the negative P is the same thing as B over A to the positive P. And when do we want to write it one way or another? You'll start to see from context, kind of like with that whole 32 raised to the 3/5 thing. Sometimes you want it one way, sometimes you want it another way. But this is a really nice way. So if you're, for instance, so let's do it. So do you have all this down? Can I erase this stuff?
Yeah.
Okay. So for instance, if I have 1 over 8 raised to the negative 3/4, I'm just going to think, well, hold up, negative with this type of thing, negative exponent with a fraction simply means flip the fraction and make the thing positive. Oh, that's easy. That's just 8 to the 3/4. Now I'm thinking, do I want to take a 4th root of 8? Or do I want to, well, let's see. I think it would be easier to, well, let's see. 8 is what? 2 to the 3rd? So let's do that to the 3/4. Now I'm thinking, okay, if I take a 4th root, I can't pull anything out of it. So that's not really going to help me. Why don't we cube it first and see what happens? So I'm going to rewrite this as 2, 3. I'm going to cube it and then take the 4th root of it and see what happens. And so let's see. 3 times 3 is what?
9.
9. So that would be 2 to the 9th right there. Again, I'm just using that right there. And so how many 2's can we pull out and how many 2's stay in?
We can pull 2 2's out and then 1 2 stays in.
There you go. 1 2 stays in. So that's the same thing as 4 times the 4th root of 2 right there. That was actually one of your homework problems. So there you go. You're welcome. No. So that's the idea there. And again, from here to here, right, I just use that fact that I could have gone, I'm going to be explicit here, right, that I had some number. It happened to be an exponent. Okay. And then I'm right, I raise it to a fractional power. I said, well, there are 2 ways of doing this. I could either think about this as the 4th root of that stuff and then cube it, or I could have gone in the opposite direction. I could take that stuff, cube it, and then take a 4th root. That's what fractional powers mean. That you could go in either order, just like you could go in either order with these guys here. And so I just kind of thought as I was going along, like, well, if I go in this way, I can't simplify that anymore because I only have 3 2's and I would need 4 in order to pull one of them out. That's not going to simplify. So why don't I go in this direction? And that indeed gave me enough 2's to be able to pull some out and simplify the expression. So that's what this is all about. You following so far?
Yeah.
Okay. One last one. Let's just on this whole negative powers thing. It says write with positive exponents, and it gives you something like this. What is that? How would you write that with a positive exponent?
Hold on.
Okay.
I don't know.
Okay. So what about this one? 1 over x to the negative n equals what? It's downstairs and it has a negative exponent. So that means what?
X to the positive end?
There you go. That's all it means. Therefore, this means what?
X to the 2 or 2/3.
There you go. That's all it is, because it says to write it with a positive exponent. It's not asking you to then say, okay, cube root x squared or cube root of x and then square it. It just says write it with a positive exponent. And that's all it wants you to do. It's that straightforward with these guys. All right. Let's do this. Now, what is this? I have a to the, let's go 5th divided by a to the 3rd. That equals a to what power? It has nothing to do with fractions.
Oh, okay. So 8 is second.
Yep. And in general, right, what we're doing here is you have a certain number of A's on the top. You have a different number of A's on the bottom. And so there's going to be some number of canceling out. And in other words, for every one on the bottom, you just subtract one off from the top. And then whatever's left over is how many you have. So in other words, right, the formula is that you have whatever the top number is minus whatever the bottom number is. And yeah, that's how that works. That's what that means. And so in general, if you have a to the n over a to the m, that's the same as a to the what?
N minus m.
N minus m. And so since that's true for whole numbers, it has to be true also for rational numbers. And so if we have, let's say, we'll do that one, 8.3 raised to the 3/4 divided by 8.3 raised to the 2/5. That's going to be 8.3 raised to the what? I don't want the final answer. Just it's going to be what in the top?
3/4 minus whatever that 2/5.
Minus 2/5. There you go. And so we're going to need to find a common denominator and do all of that work, but that's the idea right there. And it's 8.3. Don't think too hard about it, right? Like you're probably not going to be trying to reduce this stuff. Like we're just looking for the final answer. Whatever 3/4 minus 2/5 is, that is what we're looking for right there. So you're going to see stuff like that. Let's do this one. So, okay. Actually, so it's already on the board. What we're going to use is already on the board. And let's say we have 10 raised to the 3/5. And then we take that and raise that to the 2/5. That is the same as 10 to the what?
Um, 10 to the 2/5 times 3/5.
Yes, there we go, right? Because we're raising something, and so we got to multiply these exponents. That's the one right there. And so this comes out to, I guess, 2 times 3 is 6. And 5 is 25. 5 times 5 is 25. So there you go. Which, if we were so inclined, we could write it as 10 to the 6th and then the 25th root. Or we could write it as the 25th root of 10 raised to the 6th. Right? These all mean exactly the same thing. I believe in this section of the book, it's asking for the exponent, right, with a rational exponent, which is that right there. If it said to write it as a radical, well, really, you could go either way here, but this all means the exact same thing. Okay. Am I good to move on?
Yeah.
Okay. So almost the last thing that you're going to be doing for homework. We'll give you something and tell you to write it as an exponential and then simplify if necessary, then write the notation, write in radical notation for the answer. So what they mean by that, they give you this right here. Is that what they did? Yes, 8, 6, 4. So what we're going to do in this section is rewrite this as in exponential notation. So this would be a to the what over what?
Wait, can you say that again?
So they're saying to write this as an exponent. And so this is a raised to the what over what?
The 6 would it be 6 over 4?
Well, if it were 6 over 4, remember the denominator is what the radical is. It's the order of the radical. So a to the 6th over 4 would be a to the 6th. Radical would be to the 4th. So there's only one other option. This has to be a to the what?
4 over 6.
4 over 6. In general, this is how you should read these things, right? Is that whatever the radical is, and it doesn't matter if it's on the outside or inside. Really doesn't matter. These mean the exact same thing, thanks to this nifty little fact right here, is that this means the exact same thing. And so when I have something like this, I know that whatever goes in the denominator has to correspond to the radical itself. It always has to. And so if it's a 6th root, that means we're having a fraction in terms of sixths. And then you're raising it to the 4th power, or you're raising the inside to the 4th power. It all means the same thing. That's what it is. And so that's how you read these guys. So like in general, if I had B and I have a K and an M, this would be B raised to what over what?
K over M.
K over M. And I could check that and say, well, whatever's in the denominator needs to be the radical power. Yep, and that's that. And then whatever that guy is just purely raised to needs to be out there in the numerator. And so there you go. Okay, so then can we reduce 4/6?
Yeah.
What is it?
2/3.
2/3. And then it says to rewrite that, if there's some reduction that takes place, to rewrite it. And so this is a raised to what power? So first off, what's the root that this is?
2.
What's in the denominator?
Wait.
3.
Oh, I had it backwards. Hold on.
Oh, I see.
I wrote it backwards in my notes.
3 over 2. Yeah.
Wait. Yeah. Okay.
Okay, cool.
Hold on.
So, okay.
Okay. Sorry, I had it written down wrong.
Oh, no problem, no problem. So rewriting this in terms of radicals, I know, okay, I see a fractional exponent, so I know that there's a radical involved. What's the order of the radical? Well, what's the denominator? It's 3, so it has to be that. Then A is the base, okay? Raise that to what power? Well, whatever the numerator is, right there. That's what that means. Right there, that should be good. You'll be working with some ones like that. You're gonna have some uglier ones with fractions inside radicals. Might as well do one of those. Let's do that. So when you have a fraction inside a radical, we've dealt with this before. And we're doing 5, no, it's the sixth root of n to the 12th. N to the 24th. All over 64. Let me just make sure I copied this down right. 62. Okay, let me know when you got that guy copied down.
Okay.
Okay, now, big hint, just to start off with, is, well, we have a fraction with radicals. We're going to start this way. Like we've done this a bunch of times, right? Like this is how we've done this. So this is m to the 12th in the top, n to the 24th in the top. This is 64. Can we rewrite 64 as 2 to some power?
2 to the 6, is it?
I think it is, yeah, because 2 to the 5th we just said was 32. One more of them would give me 64, so that's nice.
No.
Don't need to worry about that denominator anymore. But let's just keep him like that for a second. Let's just keep him like that for a second. Okay, now, if I wanted to write just this, the sixth root of m to the 12th, that would be m raised to what over what?
Over 6.
What over 6?
12.
12. Okay, I couldn't hear you because of the boy. The boy. Yeah, you. Yeah, you. Okay. So yes, m to the 12 over 6. So let's just write it like that. M to the 12 over 6. And then what about this one? If we just have this guy by himself, 6 n to the 24, it would be n to the 24 over 6. And hey, what do you know, right? Like what I just did here, notice what I just did. I just took this thing and broke it into this and did it individually. And we know that we could do this from our previous lectures, right? Like the root of something times something is the same thing as the root of the first thing times the root of the second thing. So I just kind of skipped a couple steps here and said, well, this is equal to this. Yeah, okay. And so then I could just reduce each one of those that way. Nice. And now you might be saying, well, 2 to the 6th, the sixth root of 2 to the 6th is just 2. I could just write 2. Yeah, but let's keep this consistent, right? Like you have some number raised to some power, and then you're taking a root. That would be 2. The denominator would have to be 6 because you're taking a sixth root. And since it's raised to the 6th power, it would be 2 to the 6th. So this would be 2, 6 over 6. Hey, and what do you know? It's nice and consistent with everything we've done so far because 6 over 6 is 1. And so this does work out to just be 2. But anyway, so can I reduce m, the m part? What is that?
2 over 1.
Over 1. What is 2 over 1?
2.
It's 2. There you go. What about n? What is 24 over 6?
3. No, what, 4? Right? Wait, 6.
4. No, wait. Yeah. 6 times. How about this? 4 times 5 is 20. So 4 times 6 must be 24. So, what do we say? 4? Yeah. Man, that's the hard part. Okay, yes. 24 divided by 6 is 4. 6 divided by 6 is 1. So we should just have 2 left over. I don't know about you. I mean, but like really, that's what we've done before, right? Like if we were trying to reduce this the old way, right? And we had m to the 12, the 6th root of m to the 12th, I would say, well, rewrite that as m to the 6 times m to the 6. And you know that you get to pull 1, 2 of them out, you'd end up with 1m and 2 m's. In other words, you would have m squared. Yeah, that's exactly what we just said, right? Like, because 12 divided by 6 is 2. You're doing that, you're just doing it a real convoluted way using the old method. Ditto with the 24, right? If you had the n to the 6th root of n to the 24th, you'd say, well, how do I group that into groups of 6? And you'd say, well, n to the 6 is 6 of them, then you have 12 of them, then you have 18 of them, then you have 24 of them, a total of 24 of these guys. So you get to pull out 4 of them. And so you'd be left with n to the 4. That's exactly what you just did by doing this division right there, right? We basically said, how many groups of 6 can you make 24 into? In other words, what is 24 divided by 6? It means the exact same thing that we've been doing for the last week. And it's much more straightforward to do it this way. But can you see how it is the same thing like that we've been doing?
Mm-hmm.
Only just now we're using a little bit of formalism. We're saying, well, the 6th root means divide the power by 6. How many ways can you group this guy into 6s? And of course, if there's a remainder or something like that, that'll be left inside. This is a nice example because everything just kind of worked out. But that's the idea. That's what we're doing. Okay, we are almost through everything we need to do. 67. The last one that I'm giving you, I think numbers 69 and 73. Okay. Let's do this. So almost running over. So that's that. Let's do this. We want to write this with a single radical. This is so weird, and it's good practice, I guess. A to the 3. No, I'm sorry. It's a to the 2/3 times b to the 3/4. Oh man. Well, here's the thing, right? If it were the same power, right? Like if they had the same denominator. So let's imagine that we had a similar problem. Let's say we had 2/5 and y to the 3/5. Then we could say, oh, well, hold up. This is the same thing right here. X to the 2/5 means to take the 5th root of x to the 2. And I would say, y to the 3/5 means to take the 5th root of y to the 3rd. And then I could combine these under a single radical by that nifty little fact we had from like a week ago, which is that multiplying 2 radicals gives you that, and you'd have them both under a single radical. The problem is we do not have a common denominator. And so we need to rewrite these guys with a common denominator, which would be what? Can I erase this bottom stuff?
Yeah.
So we need a common denominator with 2/3 and 3/4. What do we want to do?
I guess the common denominator would be 12, right?
Yeah, I can't see any other way because 3 is prime, 4 is just 2 times 2, and they don't share any factors together. So the only the only recourse we have is to multiply them together. And so what are we missing over here in the denominator? Missing a 4. So we need to do the top and the bottom by 4. What are we missing over here?
3.
A 3. Okay. So I could rewrite 2/3 as 2 times 4 is 8/12. And what is B? What 3/4 we could rewrite as what?
Wait. I'm sorry, would you say that again?
Yeah, we're trying to rewrite 3/4 in terms of something 12ths.
9/12.
9/12. There we go. There we go. So now we could go through and say, aha, okay, now we have a common root. This is the 12th root. And so I'm going to rewrite this as the 12th root of a to the 8th. And we could rewrite this as the 12th root of b to what power?
9.
To the 9th. They're a common root. So I could rewrite it like that. And I think that is what it asked us to do as a radical expression. So it does want the radical right there. If it didn't want the radical, I mean, that would be that right there. Or we could even rewrite this if we were so inclined as a to the 8th, b to the 9th, all raised to the 1/12. These mean exactly the same thing. But that's not what it asked us to do. It asked us to write it like this, as a single radical expression. And I could see that, well, first off, these are both less than 1. So you're not going to be able to, like simplify that at all. In other words, we don't have enough A's to be able to pull one of them out. We don't have enough B's in order to be able to pull one of them out. And so we're done. That's that. The very last thing is 73. That one's difficult, but I don't want to say too much about it. The last one's difficult, but it's not, I mean, I would say, here's a big hint on number 73. It'll look like this. So you have 2 letters. How about Z and W? Z to the 1/2, W to the -1/2. What can we do with that negative exponent?
Make it positive.
By doing what?
Multiplying by the reciprocal.
Okay.
Right?
Well, yeah, that's how we had, that's one way of saying it, but we could say that this is the same thing as doing what?
Just making it positive.
Making it positive and doing what? Like, we can't just make it positive in the denominator. We have to make it positive by bringing it upstairs, right?
Oh, yeah, right.
That was the key phrase I was looking for, right? Okay, so let's look at this. So how then do we rewrite this guy right here? This guy's staying in the numerator. And so what do we do?
Multiply it by W to the positive 1/2.
There you go. Those are raised to the same power. In fact, I mean, we could even, if we wanted to really take this step, we could jump to the very end, but we could say, well, that means the same thing as the square root of Z times the square root of W, which is the same thing as the square root of Z times W. And that's pretty much the answer right there that you're looking for with that last question. The thing is, Z is going to look a little bit different. W is going to look a little bit different, but that's the idea, is that that's how you do it. You have something. What I usually do is, given any kind of expression, if I see negative exponents, I immediately just get rid of those negative exponents. I say, well, okay, everybody who's already positive is going to stay put, right? So these guys are going to stay where they live. The a to the third is not going to move. The d to the seventh is not going to move. But the negative means take me downstairs, in this case, make me positive. The negative down here means bring me upstairs, make me positive. Okay, cool. And now I'm in a realm that I could deal with. I've seen this kind of thing before. Whereas this is just ugly, really ugly. I don't like having negative exponents. So my first thing I usually like to do is just get rid of the negative exponents by moving things upstairs or downstairs as necessary. And that is exactly what you want to do with your, I believe it's number 73. Yep, number 73. Thing is, Z and W look a little bit different. And in the end here, you have to do some extra thinking. Okay, so that's all we're going to talk about today. You're way over as usual. You'll see her in just a minute. Okay, are you ready for homework?
Yeah.
All right. This is homework 22. Chapter 7, section 5, pages 315 to 16. Part 1. Five, 19, 35. Wednesday, so Thursday at 8.